Boy, that sure is a pretty part. Pretty garbage, am I right? Yeah, I wasn't laughing either. Hello, Internet. My name is Quinn, and this is Blondihacks. I'm working on my locomotive this week, and we're going to get back into the systems work in earnest. We took a little side quest there for some lighting and the boiler jacket, but we finished up the fire management system with the smoke box, and now we're going to get started on arguably the niftiest system of all, the steam management system, starting with the throttle body. So let's go. You've seen a steam locomotive, right? They all have these bumps on top of them. Do you ever wonder what those are actually for? Well, they actually serve a bunch of different purposes on different locomotives, but they all have one in common, and it's the most important one, the steam dome. Explaining steam technology to new folks is always a bit of a challenge because everything you were taught as a child about steam is wrong. You know, that stuff that comes off a boiling pot of water, that is not steam, that is water vapor. Actual steam, or sometimes called live steam to differentiate it, is an invisible superheated gas that carries a lot of energy, and it is no more visible to you than nitrogen or hydrogen is. Creating pure live steam, however, is actually pretty difficult. Most of it has some amount of water vapor in it, and steam mixed with water vapor is what we call saturated or wet steam, and it just kind of wastes efficiency. To convert that into pure live steam, or as we call it dry steam, you have to heat it up and or dry it out in some way. There's various ways that locomotives do this, most commonly with a superheater. Those are very cool, you should look those up, but this locomotive does not have a superheater. However, there's a much more primitive way to dry out steam that locomotives all have, and that is the steam dome. The steam dome takes advantage of very basic physics. The hottest steam in the boiler is naturally going to rise to the top, and so if you create a little pocket at the top of the boiler, a reservoir if you like, the driest steam is naturally going to collect in that little pocket. That's the steam dome. Now in this particular design of Kozo's, the dome is not an actual reservoir, but he does put the throttle body in it, and thus it acts as a collection point for the driest steam available. There are other steam collection points on the boiler for accessories and so on, and those just use the wetter, more saturated steam because they don't matter. But the good stuff, the driest steam, is reserved for the cylinders, and that's what we're going to start on today. Here on the top of my boiler, we have this great big boiler bushing, and this is where the steam dome goes. There's a whole lot of holes in that thing, so I can explain what those do real quick. There's 4 holes in the corners, and those are for mounting the throttle body that we're going to make today to this bushing. Then there's a pair of holes on either side. Those go straight through into the boiler, and those are for the safety valves. Because this is a solid fuel-fired boiler, you have to have redundant safety valves, one set a little higher than the other, so if the first safety valve fails, the second one is there to keep you from dying, because of course in a solid fuel-fired boiler, you cannot shut off the fire. This whole area is taken up by the throttle body, which connects to a long pipe that sticks back towards the cab. And inside that pipe is the actual valve stem that's attached to a handle. That's the regulator handle in steam jargon, or the throttle if you like, and that controls our steam admission into the cylinders. More detail on that in a minute, but for now, let's get going on that pipe because that's the easiest piece to make, so we'll start there. I'm sure, like many of you, I like to watch lots of different genres of people making stuff on YouTube. I like to watch, for example, boat builders, even though I'm never going to build a boat. I also like to watch hand tool woodworking because I learn a lot from those guys that actually is applicable in the machine shop. Hand tool woodworkers know a lot about body mechanics. And, for example, simply pointing my finger, as you see me doing there, does something to your shoulder and your elbow that causes it to move better and cut straighter and more efficiently. Stuff like that. It's neat. Anyway, I used to hate hacksawing, and I kind of don't anymore because the hand tool woodworkers taught me how to do it properly. I'm going to do this in the collet chuck because we're going to need 2 setups, and I want to be able to keep my concentricity from one to the other. The collet chuck can do that. And so I'll start by facing off the end, as is tradition. And I'm going to need a center in this because we're going to have to pull this out for tail support. We've got some long, skinny cuts to do. The other reason I can do this in the collet chuck is because this first operation is going to turn the body of this pipe down to a smaller dimension that happens to be a standard one for which I have a collet, so we can then flip it around and hold it by that diameter. If it ended up needing to be some weird diameter that I don't have a collet for, then I'd have to use the 4-jaw chuck, which is obviously just fine, but more hassle. Collet chuck is really nice when you can use it. So we'll get this turned down. The dimension of this is fairly important, so I'm making sure I hit it because this is going to eventually be silver soldered into a reamed hole in the throttle body. And that has to be a good fit for the silver soldering process to be successful. The next step is going to be to drill a very long hole all the way down the middle of this, and we have too much stick out for most operations. Sometimes you can get away with a lot of stick out in drilling because there's really not a lot of lateral forces in drilling, but in this case I'm going to take the extra precaution of setting up the steady rest because I don't want to take any chances on this pipe deflecting at all and or having any flex in it that might cause the drill to wander, because again, this is a very high aspect ratio hole. We've got a long way to go, and this drill has to stay on course. It's very important that it not wander. We're going to be drilling this piece from both sides because it's too long to drill from one end, and thus we got to make sure that those tunnel boring machines meet in the middle. The steady rest will buy us a lot of insurance in this regard, making sure everything stays on track. We don't actually have any machining to do on this end other than that, so that's all we needed the steady rest for now. So I can get it out of there, and we can get this part out of there and flip it around to do some features on the other end. So now I'll swap out to the smaller collet, as I mentioned, flip this part around. The other advantage of the collet chuck is that you don't have to protect the work because collets don't mar up the work the way vice jaws do. So on this end, I have to put some threads on there and some other hole drilling and so on. So I'll start by facing off the end, as is tradition. I need to face this down to the correct length because it was still a rough bandsaw cut at that point. The drawing has a length for these threads that we're going to put on it, and I'm going to use a die for these threads, so I'm going to turn down some material, even though this is ostensibly already the nominal major diameter of the thread. That's fine if you're going to be single pointing, but dies need a little bit of clearance. How much clearance a die needs is kind of varies a lot. It depends on the material and the thread pitch and many other factors. Little Machine Shop actually has a table on their website if you want to know, but honestly, like a lot of things in machining, you just kind of get a feel for it. I usually start with 5 thou under, and for something like this, a coarse thread in brass, I'll go 10 or 15 thou under. Yeah, just try it, and if it doesn't work, turn it down a little more. Then I finish drilling that through from the other end, and we're going to ream it from this end because this needs to be a really close fit on the valve stem. So this reamed hole meets in the middle with the larger diameter hole, and this end basically guides the valve stem. Now, this is the material I'm going to make the valve stem out of, so I'm doing a test fit on that to make sure I've got a good fit before I take it down, and that is excellent. That is a really beautiful sliding fit. This doesn't have to be a seal, but it should be, a nice fit anyway. There will be a seal on the end of that later, but that is excellent. Metric horns of victory for that. Now we need a counterbore on the end of this, which is going to be a sealing surface, and it has to be kind of a weird specific diameter, so I can't use an end mill or a square ground drill or any of my usual tricks for doing small counterbores. Really, a small boring bar is the only way to do it if it's an unusual diameter. And I do have smaller boring bars than this, but this one was already in a holder and it was already set up on center, so you can get a larger boring bar in a too small hole if you sort of whittle your way in a little bit at a time. Check my final dimension here. One size down from nominal is a little bit loose, and then the actual nominal gauge pin won't quite go in, so it's probably a couple of tenths below nominal, which is fine. I'm going to stop there. This is a very specific dimension in the drawings, I assume for good reasons. I took some care to try and hit that. Moving on now, that's basically it for the steam pipe. Well, that is literally it, so I can pull that out of there now and we can move on. Pretty simple component, but it did take a little bit of thought on order of operations to get all that worked out. I'm going to move on now to the main disc part of the throttle body. This thing is sort of banjo shaped, and we're going to make the body of the banjo now if you like. And I'm going to make that out of this great big thick piece of round bar. Now this is expensive material, so I don't want to waste any of it. And as you can see, it doesn't fit through my spindle bore. So we really just want to work on the end of it because we only need a disc piece. And there's a couple of approaches to this. One way is to cut a chunk off of it and just work close to the chuck, having just enough sticking out to work on. And I mean, that's fine, but it does waste material because the little stub that you're left with at the end is kind of useless. I mean, you can put it in the scrap bin, maybe find a use for it someday. The other option is to work at the end with tail support if you don't need access to the end of the part. But there's a third option, which I'm going to use here, and that's to bring in the steady rest. That'll allow me to not waste material and have full access to all surfaces on the end of the part. However, as you can see, I've got a problem. My steady rest does not clear this material. It should clear, but Well, this is a shop-made steady rest, and if I do say so myself, it's nicely made, except that I started with this casting, which is the casting from the steady rest that came with this lathe, and it's frankly not that good. It has this weird problem where the bore in it is actually not aligned with the axis of the lathe. It's a little bit too low, which means that I'm limited in how big a material I can put in it by the travel of the fingers. Now, there is actually enough room in these fingers to increase their travel a little bit, and I've been meaning to do this for years. This problem with this steady rest has bothered me for a long time, and today's the day I'm finally going to fix it. So I took that top finger over to the mill and opened that up a little bit with a large end mill, and then used a small end mill to square up the opening and get the inside corner radii that match the nut, the bolt rather, that this thing slides on. I did a whole video series on building this steady rest if you're interested, but it works really well, and now with this little change, it should hopefully get me some increased range. It was close. I didn't have to do much there, but a little bit of extra travel on that top finger, and now that slides right over that bar. Beautiful. Now, sometimes round bar stock is sufficiently good from the factory that you can run a steady directly on it, so I'll see if I can get it straightened in the jaws sufficiently to do that. But yeah, lots of tapping later, and I couldn't get it to run straight. I think it's probably a little bit out of round, and it might even have a little bit of a bend in it. Not unusual for unmachined stock. So I'm going to have to do a little extra setup work. I'll start by putting a center in the end, which we can do without the steady because it's a very small cut straight into the end. Then I'll mark out where I want the steady rest to run, and we'll cut a steady band into the part using the tail support. This is a simple matter of taking a few light cuts, just enough to clean it up so that the steady rest wheels have a smooth concentric surface to run on. We've removed a very tiny amount of material there, so we're not damaging the stock in any way or reducing its future usefulness by putting a steady band on it. And now I can get those wheels up there into contact and snug everything down, get a little looby-doob on there, and we are ready to go. You can see the run out in the end of the bar relative to where it's now running in the steady, which tells you how much out of round or bent this bar actually was, but the steady band kind of cancels all that out as far as the steady rest is concerned, and we have full access to the stock. So I'll face off the end. At this point, if you didn't want that center that was used for setup in the end of the part, you could face it all the way down to get rid of it, but we're actually going to have a use for it, so I'll leave it there, and I'll start turning the OD of this down to the dimension that we need. As you'll see, I'm not actually doing all that many operations on this part in the lathe, but I think it was worth doing all of this steady setup anyway, because one thing you learn when you start working with brass a lot is that these large diameter round bars are very expensive. Yeah, math is not in your favor when you're paying by the atom. Volume gets expensive very, very quickly as diameter increases. So 10 minutes or so to set up the steady rest with that procedure is worth it, I think. Now with that diameter set, I'm going to drill and tap a hole in the end. This is what will actually hold the steam dome down over top of the throttle body. When we're done, you won't see any of the stuff that we're making today. It's all going to be inside the steam dome. And this little threaded hole is what holds the dome down. Another great reason to use the steady in a situation like this is that we can use the parting blade when we're done. The steady is rigid enough to use any tool you want. It's just as rigid as the chuck pretty much, so it can handle the parting blade no problem. And we wouldn't be able to do this if we were using the tail support method, which theoretically we could have done there because we only needed access to a very small part of the end surface, but then we wouldn't be able to part it off like this. We'd have to take it out of the machine and over to a power hacksaw or something to cut that off and then face it down. Somewhat amusingly, I didn't quite have enough reach on the parting blade to get all the way to the center, luckily close enough that I could still break it off. I did actually check it before I started that cut, but I always forget about this clamping bolt that sticks out on the front of the parting blade. And that's actually the limiting factor on depth. And I predict that has to annoy me 5 to 6 more times before I do something about it, much like the steady. But there you go. That nice big piece of round bar can go back in the stock rack now, no waste at all. Now I'm going to flip it around and use some parallels to get it parallel to the chuck face because I want to face it down to final dimension. I didn't take a chance that I could nail that dimension with the parting blade alone and get a nice finish. I mean, that will usually work, but on a larger diameter part like this, there's more opportunity for something to go wrong with the parting cut. The parting blade could wander or something, mess up the dimension, or you end up with a bad finish. So just in case, part it off a little long, flip it around, tap it down on some parallels, and I'll face it down to final dimension. It's fairly important that the opposite faces of this part are parallel so that my safety valves that are going to mount to this are sticking up nice and straight. So I'm taking some care here to make sure that this cut is going to be parallel all the way around. And I'm holding it with some pop can there to protect it from the jaws, of course. If you're wondering, that's a Jumex can. It's a Mexican pop, and I find their cans are made of thicker aluminum than your standard Coke or whatever. So that's why I use those cans in particular. Now we've got a whole bunch of holes to put in this thing, and there's so many holes in it that there really wasn't anywhere to put parallels under it that I'm not going to hit. So I've grabbed a piece of aluminum that's been faced on both sides so they're parallel, and I'll use it as a sacrificial parallel. And I'm going to clamp it in here with this little shop-made V-block that I use for thin or small parts, just so I have 3 points of contact. It's always nice to have 3 points of contact when holding a round thing in the vise. I mean, it's not absolutely essential, but it's certainly preferable. And then I'll get this centered up on the spindle, and then we can start putting all of those fancy holes that are going to match all the ones that you saw in the boiler bushing. In the corners are counterbore bolt holes, so after centering that, I'm going to start with the square ground drill that you've seen me use a lot for making counterbores, and that's because it's got that pilot point on it, so it'll center up on the center drill, make the counterbore, and then it's going to leave a center in the bottom of that hole that I can then come in with the through hole drill, and that's going to center itself up. So very efficient. I mean, you can get dedicated counterboring tools, but I don't find them that useful in model engineering because the small counterbores you're making are always weird sizes that those counterboring tools don't come in. So I like the square drills instead. And these two side holes get drilled and tapped. These hold the safety valves. They also have a little counterbore on the top of them you can see there. That's just to make sure the safety valves sit tightly down against the surface of the throttle body. And then there's a little hole in the front that's also drilled, counterbored, and tapped, and that's for something called the snifter valve, which I'll talk about more in a minute. All straightforward operations here, just a little bit of care to make sure all the right threads go in the right places and so on. That's everything I need from this setup, so now is a good chance to take it over to the locomotive and just do a little sanity check, make sure all of my holes are going to line up, and oh no, the bolt holes in the corners don't line up, and not even really close. It's like the bolt pattern is a completely different radius. So I measured what's on there, and this is where it gets weird. The radius that I made in that bushing is 965. The radius is supposed to be 1 inch 31, which is what I did in the throttle body. And that doesn't make any sense. That's such a weird error number. It's not like I transposed some digits in the dimension. It's not like I read the dimension next to it on the drawing or substituted a different standard dimension in my head. It's just an arbitrary number that's wrong. And I have no idea how I did that. And it's enough error that there's really no getting around this. I looked at maybe just enlarging the holes a little bit so they would line up, but the error was too large. I had no choice. I had to scrap the part and do all that again. Yeah, it's never fun to scrap a part, but sometimes it's the right thing to do, and I know I say this every time, but I am always surprised at how much quicker it goes the second time. The first one took me the better part of a day to make, but the second one, I think I finished it in an hour and a half. I mean, it also helps that I didn't film the second one. Yeah, that was recycled footage you just saw, but it does always go a lot quicker the second time. Fortunately, all the other holes line up perfectly, so it's just the mounting holes in the corners. Now to get that pipe mounted on there, but I have one more problem that I knew I was going to have. I've known about this for years, actually, and that's that the boiler bushing itself is a little bit crooked. And yeah, I could tell by looking at it, it's not off by a lot, but you can see that if I mount that pipe on there, it's going to end up kind of cattywampus. So I'm going to have to do something about that. Fortunately, it's close, so all I really needed to do was, as you might have guessed, open up the holes a little bit. And I also had to open up the counterbores, of course, because those were close fitting. And as you can see, now I've given myself some angle adjustability there. And the cool thing is that the holes in the throttle body by design are larger than the ones in the bushing itself. So everything still lines up, even with the throttle body rotated a little bit. And I could have also possibly rotated the pipe a little bit instead, but that might mess up the alignment of the valve stem and so on inside with all of the internal plumbing that's in this body, so I decided it was better to rotate the whole assembly and build the throttle body to the drawings. Like I said, I knew that was going to be a problem someday, and that day was today. Now I'm going to drill a hole to solder that pipe into, and this is a little tricky to get on the x-axis because of the diameter of this. My regular edge finders won't work, but this is where the Heimer 3D probe really shows its strengths, because I can move up and down and left and right to find the high spot of the curve and the most extreme position of the curve, if that makes sense. It's a little bit more clear what I'm doing in the sped up footage, so I'm able to cycle up and down and left and right on the X at the same time until I find a spot that is the highest and left or right most. And then I can use the half function as normal to find the center between those, and then I can drill and ream for the little pocket that the pipe is going to get soldered into. I'm using gauge pins, as you see, in the two center holes, which are the good ones. Those are the ones that I did not enlarge or otherwise make a mess of, so they should be valid references. You saw me there checking the overall length of the assembly, because the drawing has a specification for that. I needed to go a little bit further in to get it a little bit shorter overall, and nailed it the second try, so feeling good about that. An obligatory chip fountain for the connected inner passages. So I get this installed there. You can see I've got a little bit of angle adjustment on it now, and I can hopefully get it straight. I'll do some sighting down the length of the locomotive. This doesn't have to be perfect because it's really cosmetic at the end of the day, but if it's off, it's going to bother me forever. So luckily I was able to get that straight. Now I need to set it up on the underside, and I'm using some gauge pins to get, again, the two good holes aligned the other direction using a parallel clamped to those pins, and I'm dialing that in, rotating the part a little bit at a time. I mean, I got this to within a thou over 4 inches or something, which is frankly ridiculous overkill for what I'm about to do, as you'll see, but I wanted to get this feature reasonably square to the part. All I'm actually doing here is milling a tiny little slot on the underside of the part, and this slot forms kind of a steam collection pocket that's on the back of the needle valve that forms the throttle itself. So this pocket is going to be over that hole in the bushing that goes straight through into the boiler, so the steam comes up into this little pocket, and then it travels down the valve stem and then past the valve seat and into this pipe here, which ultimately goes to the cylinders. There's an internal pipe in the boiler that connects that front hole to the cylinders, and then this back hole is underneath that pocket. So with that pocket cut, I can show you a little bit how this all works. You can see that little passage that goes from that pocket, that goes forward to the front hole, which is the one that goes down into that pipe that feeds the cylinders. The valve is just connecting these two holes effectively to allow steam into the cylinders. I'll get the pipe installed in the end now and slide the valve stem in there, or what will be the valve stem. This is going to have a point ground on the end of it, and that point will seat in that little passage and form the actual seal. But of course, right now it's just a stick, so it doesn't seal anything yet, but we'll get there. You can see how it works though, how that'll slide in and out and open and close the valve. Now you'll notice that front hole goes all the way through, and there's threads on the top of it. And that's actually for the snifter valve, which I'll explain while soldering these parts together. The snifter valve is a check valve that allows atmospheric air into the cylinders if the regulator is closed. Because if you suddenly slam the regulator closed while you're rolling, the cylinders are going to have a vacuum inside them, and the locomotive would slam on the brakes effectively. It would be like driving a big truck around with the Jake brake on all the time. As soon as you take your foot off the gas, your head's going to go through the windshield. You don't want that. So the snifter valve allows the locomotive to coast. If the steam is suddenly shut off, the vacuum inside the cylinders is going to pull that snifter check valve open and allow air into the cylinders so they can continue to cycle without locking up from the vacuum. I think it's more common for the snifter valve to actually be inside the smoke box, but for whatever reason, Kozo decided to hide it here inside the steam dome on the throttle body. That's why there's that kind of T passage on that front steam passage. Well, the soldering went great though. A little too much solder, as is tradition here, but that ain't gonna leak. That is a very nice looking joint. So that is ready to go back on the locomotive. I'll do one last check with the valve stem material to make sure that everything stayed aligned in there, and that looks really, really good. So the valve stem should function beautifully once we actually make it. We do need a gasket on there, so I went over to my vinyl cutter for that because the gasket is a little bit fussy. It's a little bit complicated, so I drew it up in CAD and had my vinyl cutter cut it out of the gasket paper for me. The vinyl cutter is great at that sort of thing. And the nice thing is, that's not only a perfect fit, but if I ever need another one, I can just click a button and get another one. The bolts that I'm using here, by the way, are temporary. Those will be replaced with stainless, but I have to order those because this area potentially does get wet, so don't want to use regular old black oxide bolts in there. But that is the throttle body finished in principle. I think it came out really, really nice, even if the bolt holes are secretly slightly oversized, but no one will ever know because it's only a little bit. But overall, that came out fantastic, and that's because here on Blondihacks, we do it right because we do it twice. I hope you enjoyed watching me make this. Twice. Thanks so much for watching. Thanks to my patrons for making all this happen every single week, sometimes more than once, and I'll see you next time.